Okay, so thank you all for coming. So I want to thank the organizers for organizing this conference, and hope it's going to be a very fruitful discussion of fluids, dynamics, and geometry. And thank the very influential contributions of Professor Ebin. And okay, let me just start. So I'm going to talk about a kind of general topic, so stability of twisting in 2D Hamiltonian flows. And of course, with applications to 2D Euler equations. And let me start with just sort of a reminder of how the two sort of pictures we use to view fluids. So when you have a fluid, there are basically two frameworks through which we view the fluid. There's the Lagrangian framework, which is sort of more natural, I guess. And that's where we look at the particle paths. We have like markers for each particle. The particle starts at point X at time 0. And we look at where the particle goes. And then there's the Eulerian sort of view, and which is that we fix a point that we look at and a time, and we just track how the velocity or vorticity or whatever changes at that point. Okay. And let's need to remember what I want to say. So this Lagrangian flow point of view is how this is basically how the fluid looks. Actually looks. So sometimes when we talk in Eulerian, we can talk about things being steady. Right? So we talk about a steady state of the 2D Euler equation. What we mean is maybe a state where the velocity doesn't change. So the velocity is fixed in time, but the particles could be moving in a very complicated way. So here you generally will have a lot of complexity, much more complexity than in the Eulerian point of view. And okay. In the Eulerian point of view, there's we even have stability theorems. Okay, so we have like some stability theorems. For example, you can have stability and vorticity. So vorticity is like the curl of the velocity in 2D. So we're only concerned with 2D flows here. So the general stability theorems will be of the form if you have a steady state omega star, and you consider an initial perturbation. Okay, this is small. Then it will remain small for all time. For all time. I realize I haven't written to you what the Euler equation is, but it actually doesn't matter for what we're talking about. The point is that in the Eulerian frame, when you think about the velocity field or the vorticity or quantities where you're not concerned about where the particles are actually going, you're just looking at the point-wise how the velocity behaves. You have like somewhat general stability theorems. Okay, I won't talk about the assumptions that would give you something like that. But in Lagrangian, as I pointed out, the flow map associated to a solution. So if we look at an example, so if we consider this profile u star of xy, so this is just on the 2 torus, it's sine y comma 0, right? So this is a velocity field which we just look at the top and bottom and identify them. The velocity field, so you have the arrows are pointing this way and this way, right? Right, so that may be stable in the Eulerian sense, but in Lagrangian, so if you just solve for the flow map, so you solve, like phi t dot is u star of phi t, right? So you get, okay, so phi 1 dot is sine of phi 2, phi 2 dot is 0. So you get that the flow map is just something like that. So it's not even bounded, right? So that's the point. It's not even bounded in time. Right? So it's kind of becoming unbounded. So if I give you I don't have much board space, so let me just come over here. So this should give you a picture of what I mean by complexity. So if I consider this initial line I drew here, and I consider its evolution under the flow map. So this is how it is at time equals 0. And then okay, so I unfortunately it's okay, fine. I just do. This is maybe t equal 10. Then what you get is something like this. So it's just and then it goes on the other side. You see what I'm saying? Maybe that picture wasn't so clear, but you get some spiraling due to the fact that after a long time, these particles go round and round, but they're going around at different speeds, right? So you get some spiraling. Okay, so it's not even reasonable to consider that you would have stability of something which is unbounded in time, right? It's not sort of a reasonable thing. So it's not right to say, can have stability in the Lagrangian sense in this, something like this. Okay, so I should put an asterisk by that, and okay, if someone's interested, you can ask me at the end of the talk why there's an asterisk. But you shouldn't, you just want general stability. You're not going to have stability in the Lagrangian sense. But what you could hope for is to show that the complexity is stable. So stability of the complexity of the twisting. right? So can you show, so if you have a base solution, like a steady state, which on the Lagrangian side exhibits this twisting or infinite complexity, can you prove that this is stable, right? Even to non-autonomous perturbations, right? That's the what we want to study. Okay, so let me give first a definition. So, okay, so what does twisting mean? So you can give it a precise meaning when you have an autonomous flow. So if U star is Hamiltonian, so this again, this is just in 2D and it's time independent. And it's on some 2D domain. Okay, so let's just think on some bounded domain, right? Then we know that the solutions to the particle trajectories will remain on the level sets of the Hamiltonian. So you have this thing is 0, and you have general fact that if you have a point, so let's look at a point, and we want to ask generically how do the trajectories look? Well, if this point, if psi of x is not like a critical value of psi star, so this is just some basic ODE stuff. If psi of x is not a critical value, then you know that there's a periodic trajectory going through it. And okay, most of the domain is filled with these periodic trajectories. Okay, and it can split into multiple pieces, which have, what's that? To conclude this thing, that if this, then you have a closed level set. I think you only need C1 or C2 in 2 dimensions. I think if you start with a point that's not a critical value, then it has to close. It can't do anything else. And the bound. Okay, that's what proper means. Okay, sorry. So the boundary is a level set. Yeah, sorry. Okay. And so twisting for us, like in this picture, just means that you have a picture like this. It just means that there are 2 trajectories where the period is different. That's what twisting means for us. Okay. So let me give them. What's that? In the autonomous case. Right, so the definition in the autonomous case, and this is just an autonomous definition. I guess I should be very careful for a PDE guy to talk in front of dynamicists about dynamics. So please correct me if I say anything that's foolish. So for the autonomous case, our definition of twisting means that you have 2 periodic trajectories. This is in the autonomous case, 2 periodic trajectories with different periods. Why should that be called twisting? Because, well, if you have it, okay, first of all, if you have, the only way that doesn't happen is if the entire domain is filled with periodics that are all rotating with the same speed. That's the first thing. So you can have two that are kind of close, where the periods, if it's twisting in this sense, you have two where the periods are different. So you go to a frame of the period of the inner one. So then this one just stays in some bounded region, right? And this one keeps going round and round and twisting around the inside, right? And this segment that I drew here starts to spiral around the center and becomes infinitely long and all that. Okay, so that's what I want to prove sort of stability of. So some notion of twisting like this, you want to know if it's stable to perturbation. Yes. No, they will be close. Yeah, they'll all be close. Okay. So the question is, if psi star satisfies the twisting conditions, so this is like the sort of the weak question, right? So you could ask more, but the weakest question you can ask, so can we deduce that the gradient of the flow map, okay, I forgot to say this directly, so that if it's twisting, because this thing is getting longer and longer, the gradient of the flow map is going to infinity, right? So the question is, if psi star has this condition, can we deduce that the gradient of the flow map goes to infinity for any psi, possibly non-autonomous, possibly time dependent, close to psi star? Right? That's what we want to study. So yeah. So in the case that you have a in the case that you have, okay, so I forgot to write here, sorry. So this is joint with Theo and Inji Jiang. Okay, so a very simple case of this question is it's easy to solve. So if you know that you have two fixed trajectories, so if these are closed, independent of your perturbation, which could happen if these are like the boundary of your domain, maybe these are the boundary of the domain in the original, like in the Euler equation, right? So if these are like the boundary of your domain or something like that, and they always are fixed, right? Even in the non-autonomous setting. Then if there is a difference in period here from here, then it's easy to see that even no matter what small perturbation you make, autonomous or not, these are just going to, you're going to keep the condition. The problem is that if you make a non-autonomous perturbation, you don't know that there's any closed streamline at all, right? So it may completely destroy this structure. So let me give first a counterexample. Consider this a stupid counterexample, but it's important just to point out. So consider the flow we talked about. So this definitely has twisting. And then you just add a small change in the vertical direction, small velocity in the vertical direction. Okay, so you should view this way. So you have up here particles going to the right, down here particles going to the left, and you add a tiny, vector in this direction everywhere. Okay, and now it's easy to see that any particle, okay, even though it gets pulled very, very far that way, because it takes a long time to go down here. If a particle starts up here, it's pulled very, very far that way, but then eventually it comes down here, and then it's pulled back that way, and spends some time, and it gets back to where it was, and then maybe it even goes a little bit over here, and then it goes down, and it keeps repeating, right? So this is actually completely destroys the unboundedness of the flow map, right? So the flow map in this case, phi1, if you want the formula, I hope I got it right. So maybe it's minus sign, whatever. Right, so you see that the gradients grow to size 1 over epsilon, which is natural, right? Like if you have infinite growth of the gradient in an ODE and you make a small smooth perturbation, for some time it's going to keep growing, right? So for some time it's going to grow, but then it maxes out at 1 over epsilon. Okay, so this should put some fear in our hearts, but of course this perturbation is not really, shouldn't be considered a Hamiltonian perturbation, right? Because it's not coming from it's not the gradient perp of a periodic function. It's just kind of a just stupid counterexample, if you will. Okay, so it is area preserved. It is area preserved. Because it's okay. So 0 epsilon is just it's the gradient perpendicular of like minus epsilon x, right? Right. But this is not periodic on the. This is not a smooth function on the torus, right? That's all I'm saying. So if you have a smooth function on the torus, if you're looking at really a Hamiltonian, it has a very important property, which is key to answering this question positively. That so if you consider Laplace perp of psi, okay, it's d1 psi, sorry, d2 psi, d1x, right? So it means that if I look, so the second component of the velocity, which is sending us up and down in this thing, second component of the velocity this is integral 0 on any horizontal line, right? If psi is periodic, right? It has to be. So if you go on any horizontal line, so these lines here are like the boundaries. Maybe I just make it, sorry. If you go on any horizontal line, if some particles are going up, then some others have to be going down, right? You cannot have a situation where the whole thing is just going down, right? So you have to, in order for there to be, so if you have this picture in the background, so if you have a velocity that looks like this in the background and you perturb it, okay, the enemy to the twisting is that particles start going up and down, right? They start exchanging between regions where it's going that way and regions where it's going that way, so that the flow map remains confined, right? But for that to happen, you know, the number of particles that go up always is the same as the number that go down. You see what I'm saying? So that's an important thing. If you're studying it, studying really the Hamiltonian problem, then you have this extra effect you can use.
What's the collective geometry of study? You have an area preserving flow, then it's always locally staying small enough region. But the fact that that thing is not globally the orthogonal gradient means it's not exact. There's some topological still low to the area.
Right. Right. Yeah, I mean, if you tried to, you could localize this. You could localize it to make it really Hamiltonian. You can't have globally some shift like that. Okay, so what's the theorem? So the theorem is, suppose that some psi star. Well, I suppose this is that. The answer to the question is yes. Question is yes. And the closeness is that there exists a constant depending on the background one, depending on the base state, so that if the possibly time-dependent psi is close to psi star in W11, so it means it's in L1 and its gradient in L1 is less than C0, then if you look at the flow map associated to psi, so phi t, it grows linearly in time for some constant c, again depending on psi star. It's forward and backward in time also, so it's not. And in fact, you have the same twisting idea. You do not have like closed trajectories anymore, of course, necessarily, but you still have so if I look at this restricted version of the problem where it's just, so let's just say that one trajectory is going like that, This is in psi star. Psi star. The other trajectory is going like that. Then when I unfold it, right? So when I look at it, when I really view it as a I make it 2 pi periodic in the angle variable or in x here, then you get that the flow map sends a positive measure of particles up here, positive measure set of particles down here. So if you just looked at so this is like phi star, the flow map coming from the autonomous velocity Hamiltonian psi star, then it will send these particles all the way over here, these particles all the way over here. And basically what we're saying is that it still happens in the yeah. There's no psi in that case. Okay, so I don't know how much time I have left. 30 minutes? Ah, okay. Okay. The question about psi in that case is not, what's that? The psi that's associated to the counter example is not even in W11. No, it doesn't depend on T. It only depends on X. What's that? No, this is just a statement about flow maps of a given psi. So psi doesn't have to be autonomous in the statement. Yeah. The counterexample. The counterexample, this number is infinity. Right? The counterexample, what's that?
There's a T there. I mean, W11 is an vector in space.
This is just space. And this is for all time. Yeah.
In the counterexample, psi does not depend on time, but it's not continuous on the torus. But the function is epsilon times x. When you go to the end, it has a jump. So that derivative won't exist. We'll have W11. So I was that's a little bit. Yes, yeah, I think that's what they
okay, so it's okay, it's okay. So here's how I would look at it. Okay, so in the Hamiltonian case, the second component of the velocity has to integrate to 0. Let's just think about it on the torus. Okay, it has to integrate to 0 on any horizontal line, right? In the counterexample, because it's not really Hamiltonian, right? Because in Hamiltonian case, this is a derivative of something, right? In the Hamiltonian case. In the counterexample, U2 is just a constant. You see what I'm saying?
No, that's the explanation for the statement I want, not the statement itself. But it's okay.
Okay. We can. Okay, so psi star. Okay, 1.
In the theorem here was just saying you can have any domain, but the counterexample, the picture domain, say the counterexample is pin the torus, and then now psi is not something.
Right.
It's not a
It's not a counterexample
counterexample.
to the theorem. Yeah. 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 Okay. Let me mention a few. The theorem is in any domain. Yeah, in any domain. Any domain. Yeah. Any two-dimensional reasonable domain. So if you want to pin it down, we can just fix a bounded smooth domain, but it's any domain. Okay. Let me mention some applications to the Euler equation, I think are. Yes. Yeah, I'm just saying let psi and psi star are any functions, right? It's not, they don't solve any equation. Psi star is just autonomous. That's the assumption. And psi is any functions close to it. That's it. And then I look at its flow map, right? Psi is a Hamiltonian, has a flow map. And I want to know if this grows or not. And it does. That's it. Yeah. Yes. 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 Yeah.
In terms of the Eulerian that you started off saying searching, if you took a omega star and omega naught that were close to
Yes.
L2,
Yes.
will this imply this? So if this is
This is significantly weaker than that. Yeah, this is significant. So this is implied by basically every stability theorem you prove in Eulerian in the Euler equation.
So yeah, so it's a stronger stability statement.
Yeah, I guess, yeah.
Yeah.
Yeah. Okay.
There was a hypothesis that there's this twisting.
Psi star has to satisfy. So when I wrote question means make the assumption of the question. So maybe I should have. Yeah, the base thing has to have twisting, and then the constant, the closeness depends on how far of twisting that is. Okay. Any other question? Okay. So now I'll talk about the Euler equation. Okay. So now let me mention some applications. To the Euler equation. Okay, number one, if omega star is Arnold stable. So this was the question that was asked basically. If Arnold stable, well, I won't say exactly what that means. So it just means it's like stable in the Eulerian sense. So like what I said at the beginning. Then, so here's omega star. And it either satisfies the twisting itself. So this is the condition itself, or it doesn't. Okay. If it does, then if you have any solution that starts out in a neighborhood of it, by this theorem, because it stays in a small enough neighborhood of it, then its flow map will become more and more complex, okay, in the sense that I'm saying, okay? So if omega stars, this has twisting, then the gradient of the flow map goes to infinity for all now initial vorticities, for all. So now the flow map now comes from the solution to the Euler equation. So Euler equation produces the psi dynamically, right? But if you have any point that starts in a small enough ball around omega star, its flow map that's produced nonlinearly has to go to infinity. If it doesn't have twisting, which just means that you know, so maybe let me keep things simple and just talk always about psi. I'm sorry about that. Everything, okay. If you don't know what I'm writing, then it won't make a difference to you. If you know what I'm writing, you know what I'm supposed to write. So it doesn't matter. Okay, so if psi star doesn't have twisting, then you can always perturb psi star. There exists for all epsilon. You can find a perturbed psi star, which is also Arnold stable, which has twisting. Star just means steady state for me. Psi by itself will mean some old function. Psi star is a steady state or a fixed autonomous flow. Say again? Star star is just one. Okay, so I'm just saying it's this one next to it. I need to have another one. So
is psi star star also steady?
Yes. Yes, steady and Arnold stable. Yeah. Thank you for the question, whoever said. Yeah, I mean, okay, so this you need to talk about the, the Arnold stability. There's a little bit, you need to figure out what's the right ball here. No, it's actually, because I've stated it on the stream functions, it's more like H2. Yeah, because it's really a ball in vorticity. Yeah, it's a ball in vorticity. Okay. Sorry for being a little imprecise about things. Okay, and a consequence is then, so now let me talk about vorticity. So consequence is that generic solutions to the Euler equation. So now this is in the Eulerian frame near omega star. So generic is in the sense of bare category. Yes. Yeah. Yeah, this is the epsilon, what it is. I'm sorry. Yeah. Yeah, thanks. Yeah. Okay, so generic solutions to the Euler equation near psi star in the correct sense will experience the Eulerian norm growth as t goes to infinity. And this is generic, it's in a bare category sense. Okay, so it's a little bit too much to discuss exactly what I mean, but for those who know what vorticity is, it's that generically the C1 norm of the vorticity. So if you have your steady state, that's Arnold stable, then there's a generic set of initial conditions in a ball that must go to infinity in C1. So the gradient of vorticity has to go to infinity for generic functions in a ball around omega star. Say again? And the growth is, yeah, so the growth is like t to the 1 minus. So there's a little minus you have to give up when you do this spare category stuff. Yeah. So it's bigger than 1 minus delta for any delta.
Shouldn't the two be like G? Why?
Yeah.
Why? Something's going like G.
Yeah. So actually, okay. So actually, I think you can prove t, but you don't use this bare category thing. So that this is not what you just said is not proven yet. So it should be t though. Yes. Yeah.
And you're saying okay, there's something I'm missing because of the minus. What's wrong? You just take,
So no, so you know that the gradient of the flow map goes to infinity, but you have to know something about the specific gradient, right? So when you take the gradient of omega 0 composed with phi t inverse, right? You need to have a particular direction that goes to infinity based on the direction of the gradients of omega 0. You see what I'm saying? So this is talking about the full 2D gradient, okay? I do think you can do the t, but I'm not. These are the statements that can readily be proved with this statement. Okay. Second application. Okay. Okay, I'll just take 2 minutes, I hope. So second application, which is more interesting to people doing the Euler equation, that you can consider, so there's a special class of initial, so we might as well write the vorticity equation now. Doesn't make a difference this late in the talk anyway. So the vorticity is moved by the velocity. The velocity is the solving this, and we're just going to think about this on R2. Okay, so the inverse Laplacian is just convolution with the Newtonian potential. Okay. Okay, so you can consider initial vorticities that are called vortex patches. Okay. So you can consider initial vorticity, which is just the characteristic function of a set. Okay. And the characteristic function of the set, so then the set moves. So this is, so omega 0 is just the characteristic function of the set. And then the solution is just the characteristic function of a different set. Right? And because of this, now it's been observed numerically that if you know, sort of like the, so there's an important steady state, which is the radial one, right? So you just take vorticity to be 1 on a ball. So this is a steady state of 2D Euler. It's just a characteristic function of a ball. Numerically, it's been observed that when you make perturbations, so say you just add a little, thing to it, then this will just wrap around and spiral around for all time, right? In fact, the perimeter of the patch, so the perimeter will go to infinity as t goes to infinity, right? So using this stability of twisting thing, we can give an example of an initial patch which is very close to the circular patch is a steady state, and its velocity, so let me just tell you a little bit. So its velocity is just solid body rotation inside of the ball, and then it's outside, it decays. Okay, so if you take the characteristic function of a ball, that's a steady state in the Eulerian sense, and its velocity is like this. So inside, particles go around the center. So all particles go around the center, right? All of the level sets of the stream function, all of the particle trajectories go around in circles, right? In the center, around in the ball of radius 1, they go around in time 2 pi, right? So the period inside the ball is 2 pi. Outside of the ball, because this length is bigger than 1, the period is less than 2 pi, right? So if you just look at the evolution of some kind of line, the inside will be going around like a clock, and the outside, it slows down slowly, and so this piece of this line becomes twisted around, right? So it spirals around, right? And it turns out that this vortex patch is stable. And using this idea, so you can give an example of a vortex patch, which is close to V1 of 0, for which the perimeter of the patch grows like a constant times t as t goes to infinity. Those are 2 applications. And thank you for listening.
Tarek, are there any other questions? So you've got the lower bound that's the thing on T. If you know it's Arnold stable, can you also get an upper bound that's the same border on a stable on that?
Yeah, that's a good question. Probably not, unfortunately. Probably you cannot give a better upper bound than the double exponential bound that you generally have for Euler. But so I should say that what you really would like to do is use this sort of twisting to get stronger information like mixing. And if you could do that, then maybe you'd achieve what you're saying. If you could really get some kind of mixing out of it, then you would probably be able to stop like much faster growth, and everything would just be like T. Yeah.
Tarek?
Yes.
Your perturbation for vorticities L infinity only? Or L infinity intersect L1 or something like that?
So in the
So what guarantees the example is a topology nearby, and the
Here.
topology is L infinity, maybe L
Yeah. Here it's just a small, it's a very small perturbation in L1, but it's still a single patch.
and its height is not far from 1.
Its height is equal to 1.
Okay, so it's L infinity intersect L1.
Yeah.
So there are perturbations that are long skinny ellipses
Mhm.
that are, you can make the perturbation so that the area weighted by the difference, in your case, the difference is 0. So definitely the area times the difference is 0. So the integral of the difference between the L infinity, in other words, the norm in Udovich class is small.
Mhm.
And you then create a behavior that for a long time is a Kirchhoff ellipse.
Mm.
So you have the perimeter, this is a reversible situation. The perimeter will not, it's long, but it's stable for a long time. And then these are unstable, that you can create, instability in that sense. But not the perimeter for a long time is like.
Yeah. So in this example, you have to use some topology of the omega 0. So it can't look like, in fact, it's close to the ball, but it's actually close to an annulus. It's
Right. So the main point,
yeah.
point is that you are creating an example of one kind of behavior, while other behaviors are also possible nearby.
Of course, yeah. You can, of course. So if you make, right, so the example this thing, in this sort of example, you cannot, shouldn't be expected that this thing would not spiral. But of course, if you took 1 and you deform it a little bit to an ellipse, there's a balance between how you push out and how the velocity changes, so that actually it just rotates around. Right?
Absolutely. And also, if you do an orbital stability, so if you track back, then it's stable.
Yeah.
Time 1, if you don't do orbital stability, then you discover a discrepancy of order 1 in time 1. But that's just because you're being asked too greedy.
Yeah.
All right. Very nice talk. Sorry for all this mumbo jumbo.
No, thank you.
Yes, Tarek.
Yes.
This is Gerard. Yeah, very nice talk. I also enjoyed it a lot. I'm not quite sure if this question was asked. Perhaps when some questions are asked from the audience, maybe a speaker can repeat them because they're inaudible online.
Right.
So yeah, my question that I wanted to ask was about the whether you would expect to get any better lower bound, like T to the P or something like this.
I think, I mean, as Steve was asking, my feeling is that, okay, you cannot really improve the upper bound, but the lower bound is T, I think, is the right thing.
Okay.
I mean, it's, in a sense, if you look at the whole of the fluid, if you remove small regions where there could be like hyperbolic behavior, it should be really like T. That's
right.
That's my feeling. You don't have any.
And another question I had has to do with actually a different sort of problem. I wonder if the twisting ideas and the methods that you have could be used to get something like infinite diameter of the diffeomorphism group. You know, Sasha's result.
So me and Theo have been talking about something related to that. So maybe, yeah.
Yeah, because then if you could show that some of these perturbations are twisting in your sense and are at the same time minimizing, well, that would be, of course, you'd have to control them in the L2 diameter. then that would be a nice kind of geometric, more geometric, perhaps more intuitive, less micro, local in the sense of Sasha, proof of that result.
Yeah, I think it's definitely something we're thinking tangentially about.
Okay, yeah, very nice talk. Thanks.
Yeah.
Yeah, I was just wondering, is it at all possible to tell on how the group goes in the sense that the definition of twisting just says, two periodic projections.
Yes.
I mean.
Okay. Yeah.
I realize you didn't say it, so it probably.
No, it is simple actually. So, yeah. So the question is to give an idea of the proof. Yeah, I'll just take 1 minute. That's okay. So you can look at this simplified setting that I was saying about, just like imagine that the background, like the psi star, is just a parallel flow, shear flow. Okay. You just imagine all particles are going like this. Okay. Say that you have two. In fact, Theo and I, we call this problem before this the highway problem. So you imagine that you have two highways, so like one that's speed is 1, one that speed is -1 here. And then you just try to compute. Okay, so it took us a very long time, but it's embarrassing, I guess, after the fact. You just have to compute two quantities. Compute the time derivative of the integral on the domain of two functions of this type. So F1 localizes you in the vertical direction to this region. F2 localizes you to this region. So this measures the amount of particles which are supported in this strip, right? And where they are in the horizontally. You see what I'm saying? So for F1 is maybe a bump around this value. We show that this is bigger than, like, these are the components of the flow map. The components of the flow map, as you don't view it on the domain, you view it on the unfolded domain, right? So you make it periodic. Yeah. So you have to just compute two things like this, and there's some like little bit of trickery you have to do in terms of computing this, but yeah, you just have to do that. Exactly. So that's what you're proving. When you compute this kind of thing, that's what you're proving. Yeah. There might be another proof without formulas. There also might be a proof of the Poincaré conjecture without formulas. Just saying that. Okay.
Speaker again? Now it's okay.